So hello friends, in this video I am going to discuss about second order molar placid theory. It's also called MP2 and people generally known is that as MP2. So it's in computational chemistry for researcher part 6. So in general there is a theory called Rayleigh-Schrödinger perturbation theory. So what it does, it write Hamiltonian in terms of the summation of the ground state Hamiltonian plus perturbation, and this perturbation can take order, any order. It can take one order, it can take two order, and depends on the type of potential energy that we have. Now suppose we are working with a uh, ground state of any molecule. So zeroth order Hamiltonian will be the eigenstate, or you can say it's an eigenvalue problem, and you will get the energy of a ground state. So this H0 is basically, if you are dealing with the molecular system, it will be in Hartree-Fock energy. So Hartree-Fock energy is in ground state, and your zeroth order term will be summation over the all occupied over ground state energy of the orbital energy, or you can say it is the summation of all the energy that is occupied by the orbital. So this n is basically the number of occupied orbital. So you have to sum over all the energy. Now suppose let's take in first order perturbation or first order. So first order perturbation is basically a correction, or you can say it's an perturbation operator, and this will consider the expectation values of an next next vacant orbital, or you can say E0 is it's just an correction. So now suppose we write this equation, and we will see how our Hartree-Fock energy and total energy will vary. Now if we just write it as a summation over the correction term, we will end up with again with the Hartree-Fock energy. So it means that even if you consider a first order perturbation, there will be no change in the ground state energy. The ground state energy will be the summation over Hartree-Fock occupied energy. So Hartree-Fock energy. So it is basically the sum over the energies of all the occupied orbital. So so that is why we don't have MP1. MP1 is basically the energy of an Hartree-Fock orbital. Now suppose if you take the second order correction, it will be a square term, and this will be given by this equation. So it will be summation over the expectation value of the number of the excitations you are taking. It can be singles, it can be doubles, it can be triples, and it is also inversely proportional to the energy terms. So in fact this mu 0 is a two body operator. So whenever we try to deal with the molar placid perturbation theory, we have to minimum consider MP2 correction, like or MP2 correction of order 2, that is only give the improvement over the energy. So any single excitations will leads to Hartree-Fock energy, only the double excitations will contributes towards the total energy. Now as this correction term is inversely proportional to this, so it diverges to minus infinity if this denominator is 0, and where it can be 0, if the system is having a 0 HUMO-LUMO gap, then definitely it will end up with a you will end up with a minus infinity term. So this MP2 correction will only work when there is a finite HUMO-LUMO band gap. So in general, so MP2 total energy is basically the sum of Hartree-Fock energy plus this EC is equal to EC MP2 correction term, which is summation over the occupied orbital and the double excitations you are taking. So since it is not a variational theorem, because we have not considered any wave function, and then we have just find out with respect to their, like we have their derivative with respect to their coefficient. So it is not necessary that it will end up with the you will not end up with the exact ground state. However, it is a one of the cheapest Hartree-Fock method that will allow a chemist to perform the post Hartree-Fock method with very computational with very less computational cost. So um, it is widely used in organic system, and you can also try with different system. So that is a very important concept in computational chemistry, that you do MP2 corrections and you compare it with the density functional theory, because density functional theory is an it is based on the density of an ground state. However, this MP2 correction is MP2 depends on the wave function. So it is a wave function based theory. So this is the cheapest post Hartree-Fock method. Let me just give you an example where we have just learned MP2 correction. Suppose we have an anharmonic oscillator whose potential energy is given by the equation 1, and this first term is very known because you know harmonic oscillator, the potential energy is 1 by 2 kx square. The second and third term is basically an correction term. You can say it is these are anharmonic terms. Now if you try to solve it for anharmonic term and harmonic the potential energy for these three terms, you will have the ground state energy which is given by harmonic oscillator, and if you solve it you will end up with the this value, and which is very known, like harmonic oscillator, the vibration energy is given by v v is a this is a vibration quantum number plus 1 by 2 h mu. If even if mu is 0, there will be a 0 point energy. And suppose if you solve it for h1, then you will end up with these two equations. This is an wave function, this there is like it's a you solve it for wave function, you will end up with two terms. There will be first for 1 by 6 gamma x cube plus 1 by 24 gamma 4 x4. Now if you solve it for this term, it will be an odd function and you will end up with a 0 value. So if you solve it for second term, there will be some finite value and it will be like gamma by 4 32 by alpha square. So this shows that whenever you try to do an MP2 correction, there will be there will be like term which will vanishes, as I was explaining, like in Hartree-Fock. If we just compare with the like first we are trying to add, it is vanishes. However, the MP2 correction, second order correction, will always contribute to the total energy. So total energy will be the sum of ground state energy plus the correction term. So this is the reference I have taken from Quantum Chemistry second edition and Macquarie book. So I have also mentioned it. And thank you very much for watching my videos. Please comment and try to support my work by subscribing to my YouTube channel. I hope you like my videos.